Hello and welcome again to Static 2400. This is your instructor Dr. Mayas, and today we have a new chapter. It's a chapter 9, and in this chapter we first start with studying the concept of center of gravity. This is from 9.1. The center of gravity, also referred often by CG or C. The definition of center of gravity, let's take an example with 2D problem. Let's say I have a coordinate system x and y, and I have an arbitrary body. This body has a shape. As we know, under the gravitational force G, this body does have a weight, and this weight often is located at a point in this structure, on this body. This point is called CG, right? So it's center of gravity. And the center of gravity, we can represent the total weight by a single resultant weight. We call it WR, where WR is the total weight of this body, right? Now, the question becomes, how can I identify the location of this CG, the center of gravity, with respect to any coordinate system? Typically, this coordinate system is a reference to a point in the within the body, but for now we're going to generalize this problem. So we are looking at the location from the height, y bar, and also the location in x direction. Alright, sorry, I think the audio system might have not been really great, but hopefully now it's clear. Let's try to calculate the location of CG. So by definition, what we're trying to do, in fact, find the location of this equivalent weight, which is WR. And the WR has two locations, one in x direction and one in y direction. And from the previous chapters, we discussed the centroid concept, or the equivalent location of a force. And we were able to identify that equivalency using the concept of the equivalency of the moments. Now, what we are looking for is to compute the moment of the WR. So the moment of WR about O has two portions. One is summation of the moment about the X, and summation of the moment about the Y. Now, if I want to sum the moment about of O, right? About O, but I'm looking at the moment about Y, right? You remember that this moment, if I'm looking at the resultant, it's going to be equal to the location x bar of that CG, which I don't know where it is at, multiplied by the total weight WR. However, this is also equivalent to the moment of each fragment of this object. This fragment does have a weight. Call it differential weight dW. D is a small value, and I want to calculate the moment of each differential. Now, if we want to use subscript to help us identify, if I call this is dWi, and I call the location of this dWi by xi, right? I'm calculating the moment of each of these about a point O and axis Y, right? Then I'm going to take the summation, because moment is a summation of the location multiplied or cross product dW, but because this is perpendicular, so sine theta, as in the scalar format, theta is 90, so it's 1, so we don't have to show it, so therefore it is dWi. Now, how many of these fragments we want? Now, if D means the differential and small, I can divide this weight into very, very small objects. And these small objects could be going from millions to tens of millions. So for that reason, I'm going to try to make this differential very small. So I'm going to make it going to infinity, right? To infinity. All right. So this is something we learned in the past. Now, xw means the location of CG in the x. Now, if I want to calculate the location y bar, I'm going to do the same thing, but this time I'm going to compute the moment about the x, which is this way, right? So that moment is equal to y bar, right, multiplied by wr, nothing has changed, but this is equal to I equal to 1 to infinity. Now I am calculating this yi, this is y, twi, right? Great. Now, from calculus, you learned that this can be replaced, or this is equivalent to integration. So this summation, the infinite summation, is also an integration. Recall, summation I equal to 1 to infinity of a function xi dwi. This is in fact equal to xi dwi, right? Or without, we drop the i's, xdw, right? xdw, and the boundary is from, this is an integration of the weight. So the boundary here is the volume, right? The volume. And we'll explain what's that. Actually, for now, I'm going to make it integration with respect to the weight, right? And under a certain condition, we can simplify this problem. All right, now, also recall that the total weight, the resultant weight, in fact, is equal to integral of all the element within, again, the boundary of that weight, right? Within the boundary of that weight. All right. Let's do the following. So this, with this formula, we have been able to identify the CG. So in summary, to identify the location x bar from equation 1, this is equal to x tw y bar y tw. Great. So from here you can also further simplify that x bar equal to wr is the total weight, so it can be equal to x tw over tw, and y bar equal y tw over total weight. All right, so this is, the two formulas that defines the centroid, or the center of gravity. Now we'll make this much simpler. Wonderful. Now we want to assume that our body has is isotropic, or the material property is isotropic, in the sense that the density is uniform. So suppose that the density is uniform. Now let's look into this relation between the weight, right, is equal to the mass of that body multiplied by a constant, which is gravitational constant, where G is in SI unit 9.81 meter per second square. Also, we can further simplify this problem. Now, depending on the mass relationship to its volume and density. So this is equal to the density multiplied by the total volume multiplied by G, where rho is the density, which is measured in kilogram meter cube in SI unit, and volume is the volume, and this is meter cube, right? Now if the density is constant, meaning it's isotropic, then our formula will drop as follows. So I'm going to write it as rho Vg over d rho Vg, right? Similarly for the y, which we will show. Now constant in a differential will go out and the volume will stay because it's the only variable. So this is going to be rho g x dv over rho g dv, right? dv. So what does that mean? This means I can cancel rho and g, so it's not anymore a function of that. So my x bar equal to x dv over dv. Similarly, we can do the same thing for the y, and we will end up with this formula, right? All right, so what do we call this? So in the sense when the density is uniform, we call this the center of mass, right? Or in fact, I'm gonna go back one step behind. The center of mass is defined by independent of the gravitational constant. Is defined the center of mass calculated from the following formula: x bar dm over dm, and y bar equal y bar dm over dm. Now this is center of mass. Now there is nothing really different from center of mass and center of gravity, except that the gravitational constant is assumed to be constant, and therefore went out of the integration and cancelled, and then you define the center of mass. Now going back to a simplified version of all of that is that when the density is constant, then we can write it in this form. So this is when the density is constant, and most of the occasion you will have density constant for given object, right? So this is density is constant. Okay, great. So moving on, I know the concept of integration might be some of you need some refreshment, some of you may have not taken the class, or for us, whatever reason, we'll try to simplify. So the focus is, the assumption is that the center of gravity, the calculation of center of gravity be almost identical to calculation of the centroid when the G, or when the gravitational constant of the on the Earth or in any other planet or in any other field is constant. So for that reason, we'll take some popular geometry to work on. For example, by intuition, if you look at a rectangular object, that has a uniform density. Density is constant, right? And it has width of B and or length of B and height of H. You know that by intuition that the center of mass or centroid is at the middle, right? We can prove that. We can prove that. And middle means it's located B over 2. So B over 2, and the height is H over 2. So in this case, X bar equal to, if we assume this is my Y and this is my X, and I'm located here, right? So measured from this point, X bar is equal to B over 2 and Y bar equal to H over 2, right? And we can show that. Also, we can show that the centroid, which is also coincides with the center of gravity for material with homogeneous material. If we take a rectangle, and these are pre-calculated, and so I'm going to give you the result and then work on some general problem. So this is a general triangle that has a height measured from the base by H, and it does have a base B. Now the centroid is CG or C, so coincide for homogeneous, is calculated as follows. In fact, you will find out that if we assume this to be our height, it's going to be equal to H over 3, the location of it, but you know, definitely the location in the either axis has to be determined using, you know, the formula. All right, so there are other popular geometries such as a half circle. So a half circle which has a radius r, right? The centroid C or CG is calculated from the same formula, and you will find that it's equal to 2r over pi. 2r over pi. Now, if you have quarter of a circle like that, then the CG for a radius r, so let's assume this is r, right? That's going to be equal also to the same. It doesn't matter. 2r over pi, right? Any geometry that you can see it's symmetric. I'm sorry, that's symmetric. You can use that. All right. Let's take a very simple question or problem, and then we'll expand on that. Suppose I have a rectangle like that has a length B, height H, and this is my Y and this is my X, and I want to find the centroid, right? I want to find the centroid. So by definition, we said the centroid can be calculated for a homogeneous material by locating its X bar and Y bar. So let's say this is X bar. I know I just shifted that in purpose so that we don't just assume it's at the center. So I want to find X bar and Y bar. Sorry, this is Y bar. Y bar. This is X bar. That's my CG. So X bar is equal to the integration of X dV over dV, and Y bar equal Y dV over dV, where this is dV means the volume, right? Now this is, if assume this is a 2D problem, this is equal to a depth, and let's say depth is t, and area is dA. So the volume is the depth multiplied by unit area, right? So this becomes integration over A, right? Assume T is a unit, although you don't have to assume a unit quantity, because anyway it's gonna cancel from this ratio. Or you can say it's equal to 1. But if you don't feel comfortable saying that, I can go back to my formula and say, okay, for 2D problem, this is x t dA over t dA, and similarly t y dA over t dA, right? This cancel, so it becomes, you know, just integration with respect to area. So this means that the bottom side, I want to calculate the bottom side, right? So let's just ignore that for now. So I'm gonna say, well, to calculate these quantities, I need first to know the integration with respect to dA, where, so this means find, this is equal to total area, right? This means find the total area, right? Now I understand the total area is B multiplied by 8, but let's do it in the calculus way. So how do we do it, right? Well, it's up to you how you're gonna calculate the area of a function. So we have a function B, that is bounded from 0 to B and has height h, right? So you can say, for example, that I can do the integration of a unit area, called this is dA, right? Where dA equal to a height, it looks like it's constant all the time, so it's h, multiplied by the width, dx, right? So in fact, the total area here is equal to h dx, and x from 0 to b, and this is equal h. Integration of a constant is with respect to x, this is multiplied by x, and you substitute from 0 to b, and this is equal to h, b minus 0, so this is equal to h b8, right? So this is the total area, when it's simple and we know it, right? So this is all known. All right, so what about the this quantity? What about when we are looking how to calculate these values? So we want to calculate this x dA, right? X dA. And also I need to calculate another value, y dA, right? So to be able to substitute and calculate the x bar and y bar. We'll start with the obvious one. Now, because here the value is or the function here is an x, so I want, for my best interest, to have a dA written in a format of dx, right? So I already have defined that here, dA. So the configuration of the element that I chose here is adequate. So I can write x h dx, and my limit will be from 0 to b, right? This is h over 2 x squared from 0 to b. So what I did, I integrated x, h is outside, integration of x is 1 over 2 x squared, and then you substitute h over 2 b squared minus 0, right? Now, what about the YDA. Now, to be able to do this one, my DA has or must be written in a DY, meaning I'm gonna redefine my element. So this is my X and this is my Y, right? So I want this to be written in something or as a differential of Y. So if I take this element, right, this height is dy and has a constant width which is b, right? So this one over here and different color, a different color. This is my dA and that's equal to b dy. So therefore over here I have y dA b dy. So simply this becomes b integration of y dy, and the limit is from 0 to h, right? Because from 0 to h, because I'm integrating with respect to y, and my y is this axis, so it's from 0 to h. So this is going to be equal to b h squared over 2. So this quantity is already found. Great. So in summary, what we got is following. So let me summarize the values. So what we got first, I got the total area, which is equal to dA. This was b multiplied by h. I got this integration on hand, and that was equal to h over 2 b squared, and we found also this integration, which was b h over 2, right? So we're able to do that. Now going back to the formula that we found over here, this and that, right? I'm gonna rewrite it. X bar equal to integration of x dA over dA, and y bar equal to integration of y dA over dA. So just substitute these values here. So x bar equal to, so we're trying to identify the centroid. So x bar equal, that magnitude is h b squared over 2 over b over h, and this is gonna be equal to bh squared over bh. So x bar is equal, so simplify this, it's gonna be, this cancel, so this is gonna be over 2, and this cancel, so this is gonna be h over 2, which intuitively what we know by default, right? It's just simply looking at the problem. Now this show you how to conduct this integration for a simple. Now we'll take one example with a little bit of different function and see how we can implement. So the procedure is the same. The procedure is the same, and we'll take one example. Okay, so in this problem we want to find the CG of this function x and y, and we have a function that is bounded. We are interested in finding the CG of this function, the shaded one, that is bounded from 0 to 1, and this function is y equal to x to the power 3. So the value or the magnitude of the y at 1 is y equal 1 cubed, so therefore this is also 1, right? So let's start by the definition. So you don't have to take it, as a challenge. It just is very simple. Apply the procedures step by step, and you'll be able to identify the CG. So I'll start with x bar, right? It's x dA over. So now we agree for a centroid, since this is 2D, so you don't have to put dV over the total area, and y is y dA over integration dA, right? Integration over dA. So let's start with the simple one, is how to calculate the total area, dA. Now I'm gonna take a strip over here and call this dA. According to this, dA has a width dx and has a height. Now this height is varying, right? So it is the value is here is a y, and that y depends on the location x, right? So therefore my value is equal to y, right, dx, where y is x cubed dx. So this is my dA, right? So simple. So x cubed, so the purpose is to be able to do the integration. So I was able to identify everything with respect to dx, therefore I can conduct that integration. I cannot say integration of y dx, because while this looks like a constant, but it's not, because it's dependent on x, so therefore I have to substitute x to make it look easy. So it's from 0, the boundary from dx from 0 to 1. So always the boundary correspond to the differential from 0 to 1, right? So my 0 to 1 is from here to here, it's not from here to here. So therefore the integration is, well, for polynomial, as you know, the integration is equal 1 over 3 plus 1, which is 4, and then this become x to the power 4, and you substitute from 0 to 1. So this is 1 minus, so this is 1 over 4. So this is the total area. Alright, so this is 1 down. Now while I am here, I'll be looking at calculating x bar. The reason why I want to jump into that, because I was able to express dA into this format, so therefore it's easy to plug it in here. It's easy to plug it in here and calculate x bar. So x bar, which is equal to x dA, right, over the total area. I must not do this immediately. Let me just take it slowly. Let's say I want to calculate this magnitude, right? I want to calculate this magnitude from this equation, the top one numerator. So this is equal to x, and dA is equal to x cubed dx. Alright, so how much is that? X to the power 4 dx. This is equal to 1/5. I'm just gonna be 0 to 1. So I assume that you know how to do now integration. 1 over 5 multiplied by 1 minus 0, so it's 1 over 5. Alright, great. Okay, now to calculate the integration for dA here must be written in a dy, in a differential of y. So therefore this element is not good. So I need to flip it, make it horizontal, right? Make it horizontal. So let's do it here. Can I just redraw it for clarity? So this is my X and this is my Y, and my strip, I'm gonna take it this one. So I'm looking at dy, and here's the trick. And I'm looking at the width of this from here to here. Here is 1. From here to here, this magnitude, right? This magnitude must be also written in y, because I'm looking at integration multiplied with y and differential with y. So what is it? So a point over here, I'm gonna use a different color. Point over here, y equal x cubed, right? So if I want to calculate x, I need to take the root of that. So this become 1/3 of what? Y. This will become x, or I can say x equal to y 1/3. So this is distance from here to here. From here to here, right? Now why I'm doing that? So because I want to calculate the dA. So in this sense, dA is equal to the dy multiplied by this width. This width is 1 minus y 1/3, right? 1/3. So therefore, if I want to calculate y dA, it become easier, because this one is going to be from 0 to 1. 0 to 1. The 0 to 1 is not in x, but rather is in y, because I am dealing with dy, right? So it's gonna be y 1 minus y/3 dy, right? And the integration is from 0 to 1, from here to here. Now multiply that. So this is gonna be 0 to 1 y, right, minus. Now when you multiply to a function raised to a power, you add. So this is going to be 1 plus 1/3. So this 1 plus 1/3 dy, which is equal to y minus y 4/3 dy, right? Now integration and substitution. I'm going to do this right away, so since it's easy. So this is equal to y square over 2 minus, now okay, so this is 4/3 plus 1 y 4/3 plus 1, right? And this is from 0 to 1. So doing all of this, it's going to be 1/2 minus 1/, well, this is going to be 3/3, right? So this is going to be 7/3, and this is equal to, let's do it this way, multiply it, so it's 7 minus 6/14. This is 1/14. Alright, so in summary, what we got is the following. Okay. Alright, so what we got is x bar is going to be equal to x dA over dA. From our calculation, this is simply was equal to 1/5 over 1/4, and y bar is equal to y dA over dA, and this is equal to 1 over 14 over 1 over 4. So these are the location of the centroid y bar. Okay, let's take another example. This is a little bit different. We have an object that is comprised of two components or two areas, area 1 and area 2. Area 1 is similar to the previous example we solved. It's described as a function of y equal to x cubed from 0 to 1. And we were able to find from the previous analysis how much is the x bar and y bar. So in x is 0.8 and in y is 0.2857 with in unit, let's say, meter. Now the second area, area 2, the center of gravity for that area is, because it's a rectangle, it can be figured this out immediately with respect to its local coordinates. So we know this is from here to here is going to be half, and from let's say from here to here is going to be also half, right? Half. I mean, this should be look like more square, but unfortunately I draw it as the rectangle. Now the question is, what is the overall center of gravity for this object, right? What is the overall center of gravity? So what's the equivalent center of gravity for an object that has two components, CG1 and CG2? Well, let's assume first this center of gravity locates somewhere here, right? And distinguish, I mean, not necessarily here, let's say someone arbitrary here, where x bar resultant is unknown from 0 to that point, and also y bar resultant is unknown, right? Alright, also we figure out from the last analysis that the total area for the first area was equal to 1 over 4. If was equal to 1 over 4, right? So 1 over 4. The total area for the second one is simply it's b multiplied by h, the height, so it's 1 by 1, so it's 1, right? Now the total area resultant or total is a1 plus a2, and this is equal to 4 over 4 plus 1 over 4, so this is 5 over 4. To calculate the location x bar r is similar to the concept of the concept of the moment, and this is extracted from the moment. If you multiply that by the total area, must be equal to the moment of each one, right? So it must be equal to, I'm gonna call this x1. I'm gonna call x2 bar is the location of center of the CG2, and which is, we know how much it is. It is 1 plus half, so this is 1.5. Right, this the location of the CG and x-axis, and that is equal to, I'm gonna write it down here. So the moment of the area, first one, which is 0.8 multiplied by its area, and its area was 1 over 4, plus 1.5 multiplied by its area, which is 1, and that's equal to total area 5 over 4 xr prime. So xr prime so which we don't know where it is at, is equal to this quantity. So it's 0.8 over 4 plus 1 over 5 multiplied by 4 over 5. So this is going to be your x prime. Now the y prime, the location of that resultant, follow the same fashion. So this is gonna be equal to this is the total area multiplied by the moment of each one, and the moment is equal to 0.2857 multiplied, I'm just quickly doing it, over 4 plus, now the height stays half, so it's half multiplied by the area, so that's going to be your y bar. Okay. Alright, so this way we know how to calculate for combined geometries the resultant using the same method. In next lecture we will learn more about how to do it for different sections, and we'll generalize that. But for now, someone might ask why we're doing it, what's the benefit of it? Now the benefit goes back to the calculation of the equivalent weight and the effect of the equivalent weight and on the structure or the stability of the system. And to know that, we need to know the location of that equivalent. So for that reason, I would like to go to an example. And this example, which is in the presentation file, and I encourage you all to go to the presentation file. It has some good details. I was trying also to be thorough in my presentation, giving you some steps to understand how to calculate the centroid. But going back to the presentation, in here we'll find the application of the center of gravity. Now, given this problem, as you see in the slide, this is a plate, has a thickness 0.3 and has a density, uniform density. We want to find the location of its center of mass, and also here's the calculate the reaction at A and B. Okay, so this object, as you can see, it's can be described by two pieces. A piece in the upper of the x has a function of 2x, or y squared equal 2x, and the lower is the negative x. Now the steps, we don't care about the details, but what's important is the steps that lead us to calculate, which is very important. Now first we need to calculate the center of gravity for the upper, and then we calculate the center of gravity for the lower, and then we combine them. This is similar to what I have discussed so far in my previous presentation. And after we do that, let's say we identify the location somewhere, and we know its location in x and y, and we know the total weight. Now the total weight will be the volume multiplied by the density, that's going to give us a mass, multiplied by its gravitational constant 9.81, because it's an SI unit. It's going to give us the total weight, right? That will define the location. Now after we do that, the problem become easy, because to calculate the reaction at A, well, we have here two unknown, x and y, and here we have one unknown, which is normal, right? Normal there. Now I can apply summation of moment at A, and then I'll be able to know how much is the reaction force, because the summation of moment is going to be the whatever moment of that weight, which we will know its location from A, and then we will know the moment of the unknown reaction by multiplying that unknown with the distance from here, and it's going to be a vertical or this distance from A to B, and that distance can be easily found because it's the hypotenuse of this triangle, and in this case is what you will calculate. It's a square root of 8, right? Square root of 8, this distance, and then we'll be able to calculate the reaction. So let's go over the steps, and then leave these details for you to try at home. So the first step was to calculate the centroid of this entire plate, right? You may use this approach or may divide it the way I was describing it, but let's say you were able to calculate the centroid, right, which is 1.26 and ny 0.143. So this is gonna drop into this problem. Now, drawing the free body diagram, knowing that the total weight, as you mentioned here, is equal to the area multiplied by the density multiplied by the thickness multiplied by the G, right? That's going to give you the total weight, and you can convert that in kilonewton. Apply the moment about A, right? So you're going to get the moment that from, and 1.26 is from the location of that centroid, and then the distance from here to here, right? So here 2 square root of 2 is square root of 8, which is distance. This distance, that's going to give you NB. Now you can choose to apply the summation of forces in X and Y to calculate the other unknown, which is AX and AY, and that's going to give you. So this is where you can find the best use of this centroid. There are I think more problems available for you in the textbook. You can look at them, but with this presentation we end section 9.1. Hopefully if you have questions, bring it to the class on Thursday, and I hope you guys come up with a question, because as this topic might be for some of you unpleasant, but I guarantee you it's fun to know and to apply, because you cannot ignore that in real life geometries are not really uniform in shapes or well known. Some of them are complex in shape, and the centroid or center of gravity changes, and we need to know how to calculate that so that we know the equation of equilibrium, or the reaction that is resulting from the stability of an object.